March 6, 1944, 30,000 feet above Berlin. Major James Howard throttled back his P-51 Mustang, watching the contrails of 30 Luftwaffe fighters positioning above a formation of B-17s. The numbers were impossible. One American fighter against 30 Germans, with the bombers defenseless if he didn't act. His wingmen had turned back with engine trouble. The escort from other groups hadn't arrived. The mathematics of the situation was simple and fatal. One Mustang couldn't hold off 30 Bf-109s and FW-190s. Yet for the next 30 minutes, Howard would do exactly that, exploiting a wing design that German aerodynamicists had dismissed as theoretically impossible 3 years earlier. What those German engineers didn't know, what they couldn't have predicted, was that the wing they had mocked would create the aircraft that would destroy the Luftwaffe's fighter arm more thoroughly than any bomber offensive. Within 18 months of that March morning, the P-51 Mustang would achieve air superiority over Germany so complete that Luftwaffe fighters stopped rising to meet Allied formations. German pilots would refuse combat orders, knowing that American fighters with impossible range and devastating performance were waiting at every altitude. The Germans called it der Langstreckenjäger, the long-range hunter. But it began as a rejected concept, a wing profile that violated conventional aerodynamic wisdom, designed by an engineer who couldn't prove his theories would work until he built the aircraft and flew it. The story of how Edgar Schmidt's laminar flow wing broke the Luftwaffe isn't about American industrial might or pilot courage, though both mattered. It's about how a single technical decision made in 1940 by a man German-educated engineers dismissed as a hot rod builder created the weapon that made deep-penetration bombing raids survivable and turned the air war decisively in favor of the Allies. This is the story of the wing that shouldn't have worked, the fighter that wasn't supposed to exist, and how German confidence in conventional aerodynamics became their blindness to the aircraft that would destroy them. The P-51 Mustang emerged from desperation and accident. In April 1940, the British Purchasing Commission approached North American Aviation with an urgent request: build Curtiss P-40 Warhawks under license to supplement RAF fighter strength. Britain was about to face the Luftwaffe alone. Every fighter mattered. North American Aviation, a successful manufacturer of trainers and bombers, but with no fighter production experience, seemed an unlikely choice. But Curtiss couldn't expand P-40 production fast enough. The British needed fighters immediately. North American Aviation's president, James Dutch Kindleberger, made a counterproposal that seemed insane. Instead of building someone else's outdated design, North American would design and build a completely new fighter in 120 days. The British should have rejected this immediately. Designing a combat aircraft typically required 3 to 5 years from concept to production. North American had never built a fighter. Their chief designer, Edgar Schmidt, was a German immigrant who had worked for automotive companies and had never designed a military aircraft. The proposal was absurd. The British accepted, partly because they were desperate, partly because the contract terms were favorable. If the aircraft failed to meet specifications, North American would absorb the losses. And partly because preliminary discussions suggested Schmid had radical ideas about aerodynamic efficiency that might actually work. Schmid had been studying laminar flow airfoils since the mid-1930s. The concept was theoretically elegant but practically unproven. Conventional wings generated lift but created significant drag from turbulent airflow over the wing surface. Air molecules flowing over a conventional wing quickly transitioned from smooth laminar flow to chaotic turbulent flow, creating a thick boundary layer that increased drag exponentially. Faster aircraft fought this turbulent drag with more powerful engines, which added weight, which required larger wings, which increased drag further. The cycle was self-defeating. Laminar flow airfoils promised to maintain smooth airflow much further along the wing surface before transition to turbulence occurred. If the wing profile was mathematically precise, if every curve was calculated to keep air molecules flowing smoothly, drag could be reduced by up to 40% compared to conventional designs. 40% less drag meant 40% more speed from the same engine, or 40% more range from the same fuel load. The implications for fighter design were revolutionary. The problem was that laminar flow airfoils required manufacturing precision that didn't exist in 1940. Surface irregularities as small as 1/1000th of an inch could trigger turbulent flow, destroying the laminar flow advantage completely. Rivets, panel joints, paint thickness variations, all could ruin the carefully calculated surface. German aerodynamicists at institutions like the Deutsche Versuchsanstalt für Luftfahrt had studied laminar flow extensively and concluded it was a laboratory curiosity, impossible to achieve in production aircraft subjected to combat conditions and field maintenance. Schmude disagreed. Not because he had better wind tunnel data. His data showed the same challenges. He disagreed because he believed manufacturing technology could achieve the necessary precision if the design demanded it. He would design a wing where laminar flow wasn't a hopeful benefit, but a required feature. If he couldn't build it precisely, the aircraft simply wouldn't work. This forced precision would solve the manufacturing problem because failure wasn't an option. The wing he designed for what became the P-51 was unlike anything in production. The airfoil section, designated NACA/NAA 45-100, featured a maximum thickness point significantly further aft than conventional wings, at 45% of chord length rather than the typical 25 to 30%. The leading edge was unusually thin. The upper surface had a long, gradual curve. Every dimension was calculated to maintain laminar flow across 60% of the wing surface at cruising speeds. German engineers, reviewing intelligence photographs of the prototype NA-73X in late 1940, dismissed it immediately. The thin leading edge would stall too easily. The aft maximum thickness point would create unacceptable pitching moments. The wing was too thin to carry sufficient fuel or armament. The design violated every lesson learned from Messerschmitt and Focke-Wulf development programs. The aircraft would handle poorly, stall unpredictably, and provide no combat advantage over conventional designs. British intelligence shared these assessments with the Air Ministry, which forwarded them to the RAF. Nobody changed the orders. North American was contractually obligated to deliver the aircraft regardless of German opinions. The prototype NA-73X first flew on October 26, 1940, exactly 102 days after the British contract was signed. Test pilot Vance Breeze brought the aircraft back after a 25-minute flight and reported handling that exceeded expectations. The aircraft was stable, responsive, and remarkably fast for its engine power. On November 20, 1940, test pilot Paul Balfour reached 382 miles per hour in level flight at 13,000 feet, faster than any Allied fighter in production except the Supermarine Spitfire. The aircraft achieved this speed with an Allison V1710 engine, producing only 1,150 horsepower, significantly less power than German or British fighters that were slower. The wing worked. Laminar flow was being achieved in production conditions. Drag was measurably lower than conventional fighters. The Germans had been wrong. But there was a problem that would nearly kill the entire program. The Allison engine, superb at low and medium altitudes, lost power dramatically above 15,000 feet. Its single-stage supercharger couldn't maintain manifold pressure in thin air. At 20,000 feet, where Luftwaffe fighters operated comfortably, the P-51 with its Allison engine was significantly slower than Bf-109s or FW-190s. The RAF, receiving its first Mustang Is in 1941, assigned them to tactical reconnaissance and ground attack, roles where low-altitude performance mattered. As a high-altitude fighter, the Mustang was mediocre despite its revolutionary wing. This is where accident became destiny. In April 1942, Ronald Harker, a Rolls-Royce test pilot, flew a Mustang at the RAF facility at Duxford. He was stunned by the aircraft's handling and speed at low altitude. Then he asked a question that would change the air war. What would happen if the Allison engine was replaced with the Rolls-Royce Merlin, the two-stage supercharged engine that powered the Spitfire IX? The Merlin produced slightly less horsepower at sea level than the Allison, 1,515 horsepower versus 1,520 horsepower. But the Merlin's two-stage supercharger maintained power to 25,000 feet and beyond. If Schmud's low-drag laminar flow wing could be combined with an engine that maintained power at altitude, the resulting aircraft would have performance advantages over every fighter in service. Rolls-Royce installed a Merlin 65 in a Mustang I as an experiment. The aircraft, designated Mustang X, first flew in October 1942. Performance was extraordinary. Maximum speed increased from 390 miles per hour with the Allison to 432 miles per hour with the Merlin. Service ceiling increased from 30,000 feet to 42,000 feet. Rate of climb nearly doubled. The laminar flow wing, finally paired with an engine that could exploit its efficiency at all altitudes, created an aircraft that could outperform anything Germany had in production. North American Aviation immediately began converting the P-51 design to use the Packard V-1650, the license-built American version of the Merlin. The resulting P-51B entered production in June 1943. By December 1943, P-51Bs were arriving in England and beginning combat operations with the 8th Air Force. The early missions revealed the Mustang's true revolution: range. The low-drag laminar flow wing wasn't just making the aircraft faster, it was making it dramatically more fuel efficient. A P-51B with two 75-gallon drop tanks had a combat radius of 750 miles. For comparison, the Republic P-47 Thunderbolt, the primary USAF escort fighter in late 1943, had a combat radius of 475 miles even with drop tanks. The P-51 could fly 275 miles deeper into Germany and still have fuel for combat and return. This solved the strategic problem that was killing the daylight bombing campaign. Throughout 1943, USAF B-17 and B-24 formations had been sustaining catastrophic losses when they ventured beyond fighter escort range. The Schweinfurt raids in August and October 1943 demonstrated the crisis. On October 14, 1943, 291 B-17s attacked ball-bearing factories at Schweinfurt without fighter escort for the final 400 miles. Luftwaffe fighters shot down 60 bombers and damaged 138 more, a 20% loss rate that made unescorted deep penetration missions unsustainable. General Henry Hap Arnold, commanding the USAF, understood that daylight bombing would be abandoned unless fighters could escort bombers all the way to targets deep in Germany. But existing fighters couldn't reach that far. The P-47, despite being an excellent aircraft, was too heavy and had too much drag to achieve the necessary range. The P-38 had the range, but was vulnerable to German fighters at high altitude and suffered from engine problems in cold weather. The P-51, with its laminar flow wing giving it range no conventional fighter could match, was the only solution. In January 1944, P-51 groups began escorting bombers to targets that had been beyond fighter protection. In January 11th, Mustangs escorted bombers to Brunswick, 450 miles into Germany. On March 3rd, they reached Berlin for the first time, an 1,100-mile round trip. On March 6th, Major James Howard's solo defense of the B-17 formation demonstrated not just courage, but the aircraft's combat performance against overwhelming numbers. Howard's tactical report was remarkable in its technical detail. Engaging 30 Luftwaffe fighters for 30 minutes, he destroyed 4 confirmed and damaged several others. But his report focused on how the P-51's speed and maneuverability allowed him to dictate every engagement. When German fighters tried to dive away, he could follow them. When they tried to climb, he could follow them. When they tried to turn, he could turn inside them. The laminar flow wing gave the Mustang such low drag that it could out-accelerate and out-zoom German fighters despite having less engine power than an FW-190. Luftwaffe pilots, encountering Mustangs in combat for the first time, reported an aircraft that seemed to violate physics. German intelligence had assessed the P-51 in 1942 and concluded it was a tactical reconnaissance aircraft with good low-altitude performance but limited high-altitude capability. By March 1944, that assessment was catastrophically wrong. The P-51B with its Merlin engine was superior to German fighters in every performance metric except rate of roll and instantaneous turn rate, and even those advantages were marginal. Major Erich Hartmann, the highest-scoring ace in history with 352 victories, encountered P-51s on the Eastern Front in early 1944 after transfer from a unit that had fought them in the West. His tactical assessment, recorded in a post-mission debriefing, was brutally honest. The American fighter has no weaknesses. It is as fast as our aircraft in level flight and faster in a dive. It can climb with us. It can turn nearly as well. Its armament is as effective as ours. But it has one advantage we cannot counter. It can fight at full power for hours, while we must husband our fuel for minutes. This makes every engagement favor the Americans. They can afford mistakes. We cannot. The fuel efficiency advantage was fundamental. A P-51B cruising at 25,000 feet consumed approximately 50 gallons per hour. At combat power, consumption increased to 100 gallons per hour. With internal fuel of 184 gallons plus 2 75-gallon drop tanks, a Mustang could fly for over 6 hours, spending 1 to 2 hours in combat and still return to base with reserve fuel. A Bf-109 G6, by comparison, had internal fuel of only 88 gallons and consumed 72 gallons per hour at cruise, 156 gallons per hour at combat power. Maximum flight time was 90 minutes, with perhaps 15 minutes of combat time before the pilot had to consider fuel for return. This meant that Luftwaffe fighters engaging P-51 escorts were on a timer from the moment combat began. Every minute of fighting consumed fuel that couldn't be replaced. Every evasive maneuver, every high-power climb or dive reduced the time available before disengagement was mandatory. The Germans were fighting with reserve fuel lights illuminated, while Americans operated with full tanks. This psychological pressure compounded the tactical disadvantage, forcing German pilots to make hurried decisions that increased their vulnerability. The laminar flow wing created this advantage through pure aerodynamic efficiency. At cruise settings, the wing maintained laminar flow across approximately 60% of its surface, reducing total aircraft drag by 30 to 35% compared to equivalent conventional designs. This allowed the Merlin engine to run at lower power settings for the same airspeed, consuming dramatically less fuel. In combat, when power settings increased and laminar flow was partially disrupted by high angles of attack and maneuvering, the wing still maintained superior efficiency compared to turbulent flow designs. North American Aviation engineers analyzing gun camera footage and pilot reports discovered that the laminar flow wing had an unexpected additional advantage: high-speed handling. The wing's pressure distribution, with its aft maximum thickness point, delayed compressibility effects at high speeds. P-51s could dive past 500 miles per hour indicated airspeed before encountering buffeting or control problems. German fighters, particularly the Bf-109, experienced severe compressibility effects above 450 miles per hour, with controls becoming heavy or frozen. This meant that in a high-speed pursuit dive, a Mustang could follow a German fighter until the German either slowed down, making himself vulnerable to gunfire, or continued accelerating until control effectiveness was lost and structural failure became probable. Luftwaffe pilots began reporting a phenomenon they called Mustang fever, the psychological dread of engaging American long-range fighters. Unlike the P-47, which could be avoided by climbing above its effective altitude, or the P-38, which could be defeated in turning combat, the P-51 was everywhere, at every altitude, in numbers that grew larger each month. By April 1944, 5 P-51 groups were operational with the 8th Air Force. By June, 8 groups. By September, all 14 escort fighter groups in the 8th Air Force flew P-51s. The aircraft that German engineers had dismissed as aerodynamically questionable was being mass-produced at a rate of 500 per month. The industrial achievement was as remarkable as the technical design. The laminar flow wing required manufacturing precision that was unprecedented in 1940. North American Aviation's solution was to over-engineer the production process. Wing skins were precision-formed in hydraulic presses to tolerances of 0.001 inches. Flush riveting techniques were refined to eliminate any surface protrusion. Panel joints were precision ground. Paint was applied with thickness monitoring that ensured uniform surface. The result was that production P-51s maintained laminar flow characteristics that matched or exceeded the hand-built prototype. This was the manufacturing precision that German engineers had said was impossible in mass production. American industry achieved it by treating aerospace manufacturing with the same precision techniques that produced automotive engines and scientific instruments. At peak production in 1944, North American Aviation's Inglewood plant in California was completing one P-51 every 47 minutes. A second plant in Dallas, Texas, was producing one every hour. Both plants maintained the precision manufacturing that laminar flow demanded while achieving production rates that would have seemed impossible in 1940. The aircraft that was supposed to be impossible to build in mass production was being manufactured faster than Germany could replace fighter losses. The strategic impact accelerated through 1944. With P-51 escorts able to accompany bombers throughout their missions, Luftwaffe fighters faced an impossible choice: engage the bombers and face escorts with superior numbers, performance, and fuel endurance, or avoid combat and allow bombers to destroy German industry unopposed. Luftwaffe fighter losses increased catastrophically. In February 1944, the Luftwaffe lost 33% of its fighter pilots on the Western Front. In March, 56%. In April, 43%. These were unsustainable losses for a force that couldn't train replacements fast enough. The qualitative gap widened as experienced German pilots died and were replaced by inadequately trained novices. The average Luftwaffe fighter pilot in 1944 had less than 50 hours in type before entering combat. American pilots arrived in Europe with 200-plus hours in type, extensive gunnery training, and tactical instruction that included studying gun camera footage from actual combat. This training advantage, combined with aircraft superiority, created a death spiral for the Luftwaffe. German pilots died before gaining experience. Survivors faced increasingly impossible odds. Unit cohesion collapsed as losses mounted. Major Heinz Baer, a Luftwaffe ace with 220 victories who survived the war, described the summer of 1944 in his post-war memoir. "We knew we were fighting a lost battle. Every morning we took off knowing most of us would not return. The Americans came in formations of hundreds, protected by fighters we couldn't defeat. Our Me-109s and FW-190s were excellent aircraft, but the Mustang was better in every way that mattered. The laminar wing gave it speed we couldn't match and range we couldn't counter. When we attacked the bombers, the escorts were waiting. When we tried to disengage, they followed us down. The only question was how long we would last. For most pilots, the answer was measured in days." By September 1944, the Luftwaffe had effectively lost air superiority over Germany. Daylight belonged to the Allies. P-51s roamed German skies at will, strafing airfields, trains, and road convoys. The long range that made them effective bomber escorts also made them devastating ground attack aircraft. A P-51 group could escort bombers to a target 500 miles away, fight off interceptors, then strafe ground targets on the return flight and still land with fuel reserve. German ground forces learned to halt all movement when American fighters were overhead. The psychological impact was as devastating as the physical destruction. The technical reason for this dominance remained the wing Edgar Schmood had designed in 1940. Every advantage the P-51 possessed, its speed, its range, its high-altitude performance, its fuel efficiency, derived from the laminar flow wing's reduced drag. The Merlin engine provided power, but engines were interchangeable. Other aircraft used Merlins and didn't achieve P-51 performance. The wing was unique, and it had been rejected by German engineers as impractical. Post-war analysis by British and American aerodynamicists confirmed that production P-51s achieved laminar flow across 55 to 60% of wing surface at cruise conditions. This was unprecedented for mass-produced combat aircraft. German attempts to achieve similar results had failed because their manufacturing tolerances weren't adequate. The Germans had the theoretical understanding, their research into laminar flow airfoils was excellent. They lacked the industrial capacity and quality control to build wings that met the required precision consistently in combat aircraft production. This represented a fundamental difference in industrial philosophy. German aircraft manufacturing emphasized skilled craftsmen producing relatively small numbers of highly capable aircraft. Quality came from expertise and hand-fitting. American aircraft manufacturing emphasized precision tooling and process control, producing large numbers of standardized aircraft with consistent quality. When the design demanded precision that exceeded what skilled craftsmen could reliably achieve by hand, the American system had the advantage. The P-51's production totals reflected this advantage. From 1941 to 1945, North American Aviation produced 15,686 Mustangs of all variants. The laminar flow wing, identical in every aircraft, maintained its aerodynamic properties throughout the production run. By comparison, Germany produced approximately 34,000 Bf-109s and 19,000 FW-190s during the same period, but German production quality declined steadily after 1943 as material shortages, labor problems, and bombing disruption affected manufacturing precision. The ultimate validation of Schmood's design came not from performance statistics, but from German attempts to copy it. In late 1944, Focke-Wulf engineers began designing the TA-152, an advanced fighter intended to counter the P-51. The design incorporated many features observed in captured Mustangs, including a high aspect ratio wing with laminar flow characteristics. But by the time the TA-152 entered production in January 1945, Germany lacked the manufacturing capacity and materials to produce it in meaningful numbers. Fewer than 200 were built. The aircraft that might have matched the Mustang arrived too late and in too few numbers to matter. At the Smithsonian National Air and Space Museum in Washington, D.C., a P-51D Mustang hangs in the World War II gallery. The placard describes its service record: 15,686 built, 4,950 lost in combat, credited with 4,950 enemy aircraft destroyed in air combat, and 4,131 on the ground. But these numbers don't convey the strategic impact. The Mustang didn't just destroy German aircraft, it destroyed the Luftwaffe's ability to defend German airspace, which enabled the bombing campaign that destroyed German industry, which made German defeat inevitable. The wing that created this aircraft was rejected by experts. German aerodynamicists dismissed it as impractical. British engineers were skeptical. Even American aerodynamicists questioned whether laminar flow could be maintained in operational conditions. Schmood built it anyway, not because he could prove it would work, but because the mathematics suggested it should work if manufacturing was precise enough. Then he forced manufacturing to be precise enough by designing an aircraft that couldn't work any other way. This is the engineering philosophy that won the air war. Not superior science, German aerodynamic research was excellent. Not superior individual aircraft quality, German fighters were well designed and well built. But superior industrial integration of advanced concepts. The Americans took theoretical aerodynamics that everyone understood and built it in mass production with precision that everyone said was impossible. Then they built 15,686 of them and sent them to Europe with pilots who had been trained for 200 hours to fly them effectively. The Luftwaffe broke not under the weight of American numbers alone, though numbers mattered. It broke under the weight of American technical sophistication applied through industrial mass production. The P-51 Mustang was the embodiment of this approach, a revolutionary wing design that demanded manufacturing excellence combined with the industrial capacity to build thousands while maintaining precision, combined with the training infrastructure to produce pilots who could exploit the aircraft's advantages. Major James Howard received the Medal of Honor for his March 6, 1944 defense of the B-17 formation. The citation emphasized his courage, one pilot against 30 enemy fighters. But Howard's own after-action report emphasized his aircraft. He could fight 30 Germans because the P-51 gave him speed, maneuverability, firepower, and endurance that let him dictate every engagement. He was courageous, but courage without tools is just sacrifice. The laminar flow wing gave him tools that made survival possible and victory probable. By May 1945, when Germany surrendered, the P-51 had achieved air superiority so complete that Luftwaffe fighters rarely challenged Allied formations. German pilots who survived the war reported that orders to intercept bomber formations were essentially suicide missions. The Americans had too many fighters, too much fuel, too much training, too much of everything. But the foundation of that superiority was an aircraft that shouldn't have existed according to conventional aerodynamic wisdom. The rejected wing design created the plane that broke the Luftwaffe. German engineers mocked it as aerodynamically impossible in 1940. By 1944, they were trying desperately to copy it while being systematically destroyed by the 15,000-plus examples that American industry had produced. The mathematics of laminar flow were correct. The engineering to achieve it in production was possible. The industrial capacity to mass produce it was available. The strategic impact was decisive. Edgar Schmude, the German immigrant engineer who designed the wing that destroyed Germany's Air Force, never received the recognition his achievement deserved. He continued working in aviation after the war, designing the F-86 Sabre that dominated the Korean War using aerodynamic principles refined from the P-51. He died in 1985, largely unknown outside aerospace engineering circles, while the aircraft he designed became legend. The P-51 Mustang remains the iconic American fighter of World War II, celebrated for its performance and its role in achieving air superiority. But the celebration focuses on pilots and missions, on individual courage and tactical victories. The technical foundation of those victories, the wing that Edgar Schmude designed when everyone said it couldn't work, is engineering history, acknowledged by specialists, unknown to the public. This is the pattern of technological warfare. The weapons that win wars are celebrated. The engineering decisions that created those weapons are footnotes. The laminar flow wing that gave the Mustang its revolutionary range and performance was as important to Allied victory as the Norden bomb sight, radar, or the atomic bomb. But it's remembered, if at all, as a technical curiosity in an aircraft that's famous for other reasons. The Germans laughed at the impossible wing in 1940. By 1945, German laughter had died with the pilots who had fought against what that wing created. The Luftwaffe, once the most formidable air force in the world, was reduced to flying old men and boys in obsolete aircraft on desperate missions against overwhelming numbers. The Americans, flying aircraft built around a wing design that violated conventional wisdom, owned the sky. One engineer's rejected design, 15,686 aircraft, air superiority over Nazi Germany, the strategic bombing campaign that destroyed German industry, victory in the air war, all from a wing that shouldn't have worked but did, built with precision that was impossible but wasn't, manufactured in numbers that were unthinkable but weren't. The mathematics were correct, the engineering was sound, the manufacturing was precise. The Germans were wrong. And because they were wrong about one wing design, they lost the air war. The thunder wasn't from machine guns or bombs, it was the whisper of laminar airflow over 60% of a wing surface, reducing drag by 35%, extending range by 300 miles, making possible what was impossible, destroying what was undefeatable, winning what was unwinnable. Quietly, efficiently, decisively. The rejected wing broke the Luftwaffe, and Germany never knew why until it was too late to matter.